How's it going, guys? It's Ashton here again, and now here on Python, in order to simulate collecting data, and then we're going to use two regressions in order to model our data, and then we're going to put that data into a 3D data plot. And so the first thing we're going to do here is actually we're going to use import our data packages we're going to be using today. So the first import we're going to use is NumPy, which is just numerical Python, and we're going to store that as NP. The next thing we're going to do is from plotly underscore subplots, and we're going to import make subplots. And what this is going to do is allow us to create different subplots or graphs of our data, and then what we can do is we can use that compare side-by-side comparison of those. We're going to import plotly dot graph underscore objects as geo, and this will just let us import our regression data that we're going to be creating into our graphs. And then the next thing we're also going to import is we're going to import plotly.io, and then we're going to store that as an IO or PIO. And what we're going to do is this is going to allow us to modify the default template of our Plotly graphs, and I want to use the dark graphs because I think it stands out better and allows us to see the data on the screen better. Plus I like how the black graphs look. So we're going to import plotly.io, and then we're going to as PIO, and then PIO.template underscore default. I'm going to store that as plotly underscore dark, and this will just make our graphs dark. And then import, we're also going to import our, we're going to import SciPy. And then what SciPy is going to do is it's going to allow us to actually use the minimize function import, which is part of SciPy, and we're going to use that for the Penrose pseudo method that we will be doing later. So we import SciPy dot optimize no, from, I'm sorry, not from, import, we're gonna from we're going to import the minimize function. My bad, plotly make subplots. Subplots. Oops. Alright, with all the imports from our Python libraries added in, now what we're going to do is create some experimental data, And then the way we're going to do this is we're going to simulate the data collection by gathering random numbers in a uniform distribution. And so the first one we're going to look at is our Reynolds number. So we're going to do Reynolds number is equal to NP excuse me, dot random, and then dot uniform. And then what we're going to do is we have for our Reynolds number, we have our lower bounds. So we want our lower bounds to be 2,000, so 2e to the third, and then we want our upper bound to be 3,500, or just 35 to 10 to the third, and then we want 100 values for our Reynolds number. We're going to do the same thing for our Schmidt number, which is going to be SC equals NP dot random dot uniform, and then for our Schmidt number, we're actually going to run it from 0.2 and with a max of 2.5, or I'm sorry, 0.6 to a max of 2.5. We're going to also have another 100 values there. And then for our now what we're going to do is put in the Sherwin relationship. So SH is going to be equal to, and then from the textbooks we have the set equation that it gives us. We also have the Sherwin relation from this, so it's going to be 0.023 times our Reynolds number, which is going to raise the power of 0.83. We're going to multiply that by the Sherwin number, which is going to be raised to the power of 0.44. And what else we're going to do is we're going to normalize our experimental data, and to do this we are going to use the normal distribution np.randomize, or not randomize, but random dot normal. And what it's going to do is it's going to ask us for our local median or mean value, which is going to be just our Sherwin number, and that will just be what our data is centered around. And it's going to ask us for the scale or the standard deviation, and we want that to be equal to a 10% distribution of our Sherwin number that we're going to be using. So 0.1 times our Sherwin number. I'm going to hit enter, and then everything's good there. So now what we're going to do is we are actually going to use the linear regression method in order to turn a relationship, and then we're going to be doing that via matrix manipulation. So the first thing we need to look at is when we think about the Sherwin relation that we established from part 1, we saw that we had, and I'll put it on the screen right here, we had that SH equals some constant A times our Reynolds number raised to the power B times our Sherwin number, our Schmidt number, I'm sorry, raised to the power C. And what we're going to do is we are going to take the natural log of both sides in order to get the natural log of our Sherwin number, which is going to be equal to the natural log of A plus B times the natural log of our Reynolds number plus C times the natural log of our Schmidt number. And then what we're going to do is we are going to put that into a design matrix based off those things. And in the first column of our design matrix, we're actually going to have all ones, and those are going to represent the number for our A value. So what we're going to do is we are going to say that np dot ones and then underscore like. And what that's going to do is going to create the same amount of ones as we have the number of Reynolds numbers and Sherwin or Schmidt numbers. So we're going to set that equal to RE. When we hit enter, it creates basically just an array of all ones, and it's 100 ones. And what we want to do is actually put that into our design matrix with the natural log of our Reynolds number and our Schmidt number. So what we can do is we can call this variable x. So we x equals np dot a column stack. And what that's going to do is it's going to allow us to put every variable into an array, and we can lay them side by side. So you'll see here in a second, when we put these values into an array, so the first component of our array is going to be our ones and or the constants for the natural log of a term, and our second variable is going to be the natural log of our Reynolds number, so np.log of re. And then the third component is going to be the natural log of our Schmidt number, so np.log of c. And then we're going to close out our array and then close out the entire bracket, so we hit Shift Enter. Everything looks like it worked, and then when I hit display x, we can see that we have a column of ones and then a column of the natural log of our Reynolds number and the natural log of our Sherwin number. So what we need to do now is we know that when we take this design matrix and multiply it by our coefficients and or exponents, that it's going to give us our Sherwin number into an array as well. So what we have to do is actually create an array that's going to be equivalent in size, and the one way to do this is by multiplying both sides by the the transpose of our first array, or our first matrix, I should say, of x. So then with that transpose multiplied by both sides, we'll have the Sherwin number multiplied by the transpose of x plus our unknown, which is going to be the log a, and then our bc variable multiplied by transpose multiplied by our matrix of x. And then one way to get rid of this on our side with our unknown is to basically multiply by the inverse. So what we can do is we can set u, so our unknown, we can set that equal to np.linearalgebra, and then underscore that inverse, or dot inverse. And what we're going to do is multiply our transpose, so which in Python is listed as n.t, and then for matrices and how to multiply them, we use the @ symbol, and we're going to multiply that by x, which is our original matrix, and then that's also going to be multiplied by our matrix again of x. And then this is also going to be multiplied by, or I should say the transpose of x, because we had to multiply the transpose by both sides to be equivalent. And multiply that by the natural log of our Sherwin number. And then what we're going to do is we're going to print our u, and we're also going to print the exponential version of the first component of our matrices of our u, because that first component, like I said, is going to be the natural log of our a value, and since we want that a value to its regular value, we want to take the exponent of it to be e to the natural log of a to give us just the a value itself, and that's in component 1 of our matrix or array. So exponent of u, and then our first element of our array. parentheses. Alright, so looking at the variables that were given here, we can see that the 0.839 is pretty close to the 0.83 that the value that the textbook gives us for our b value, and then the 0.48 is fairly close to the 0.44 from our textbook value again, and the a of 0.020 is pretty close to the 0.23 value for our a value. So with this error that we're seeing in the difference between them can be attributed to the 10% normality distribution of our experimental errors that we used to create our random variables or our random values for our Reynolds and Schmidt number. So this is just why we're seeing the discrepancies in said value numbers, but in all intents and purposes they are fairly similar. And then now we are actually able to start with our second method, which, like I said earlier, was going to be the Press-Ross-Pizzuto method, and that's going to be the method of least squares. And we're going to want to minimize that for our values and everything like that. So what the first thing we're going to do is we're going to define a function. We're going to call it squares. Excuse me. I'm sorry. We're going to call it sum of our squares. And then for that, I'm just going to use the term x, because you can use any variable. It's just asking for any variable. And we also want it to return the value. So we're going to return and then np.sum, because we want the sum of our squares. And then our first term is going to be our Sherwin number. Oops. And we're going to subtract the difference in our values of our A and B and C terms. And then what we're going to do is basically say that we're going to take the first component of our X array for A values, multiply that by our Reynolds number raised to the power of the second component of our A. And then we're going to multiply that by our Schmidt number raised to the third component of our sum of our squares. That's 2. And we don't need an A there, we need an X. And then what we can't forget is to actually square this. And then what we're going to do is we want to minimize. So we want to minimize the sum of our squares. So minimize and the function, since we call it sum square. And then it's going to want the initial values that we should be obtaining. So our first value is going to be 0.023. The second value is going to be 0.83 for our B value. And our C value from the textbook equation that we know is going to be 0.44. Shift enter. Double scalar. So it looks like I did something wrong. Hold on a second. Show number. Oops. Going to square the inside of their terms, not our Sherwin number or Schmidt number. Alright. So when we look at these values, we see a 0.22 for our A, which is fairly close to our numerical values that were given from the textbook. Then we see for our B value, we get 0.83, which is very close to our 0.83 from our textbook, and then we get 0.48, which again is very close to our 0.44. So now that we have these two regressions calculated, we are going to go and move on to the graphing portion of our exam or our data in order to see it in 3D model. So I will be right back.